Hello and welcome to another video. In this video we're going to be working on design hash map. So we want to design a hash map without any built-in hash table libraries where we can initialize, we can put key value pairs into the hash map. If the key already exists, we can update it, and we can also get the value which the key is mapped to, or -1 if there's no mapping, or we can remove the key and the corresponding value from the hash map. So I'm just going to briefly talk about how a hash map works, and there are going to be some things you could do to make it more or less performant. And we're just going to go with a reasonable implementation, not something super insane. Obviously not something like, a native Python hash map would be, because that would be way too performant and way too much code. But briefly talk about kind of roughly what happens. So essentially, usually a hash map is implemented with an array. So you have some kind of array, and it has some buckets, right? So let's say we just start with some array with, let's say, 5 or 6 buckets or whatever. And you have some kind of hashing algorithm. So you take a key, it goes through a hashing algorithm. So hashing algorithm. And then you get some kind of an index. And for that index, you store your key value pair. And you can store this in a bunch of different ways. So usually it's implemented where the bucket, and a bucket is every single, so the data structure in this actual array. Usually they either store as a linked list or another array. And so pretty much, let's say you have some key 5, and you run it through your hashing algorithm, you get some index 0. Then what's going to happen is you go to this index 0, and then whatever data structure you're using here, either a linked list or an array or whatever it is, you need to check, does this key already exist in whatever way you want. So you can either do this with a linked list where you would go through your linked list and you would check, or you can have an array, or you can have a sorted array. There's a bunch of optimizations, right? It's a super open-ended question here. But essentially, you just look if your key exists, and then you can store your key value pair once again as an array or a tuple or whatever kind of you want, right? It's personal preference there. So you check if your key exists in that bucket, and then if it does exist, you update the value, and if not, then you also add it to whatever data structure you have, like I said, linked list, array, or whatever you have. So that's kind of how it works. And then for performance issues, we can talk about it briefly. Essentially, something optimal would be having some kind of small hash table, right? And you can kind of figure out how many open buckets you have left. And then once your number of open buckets left is kind of low, then you probably want to have you probably want to add space for your hash map and maybe relocate your elements. This is super open-ended, and this is it can get super complicated super quick, right? In terms of performance. It's like when you make an array, you give it some size, and then when it's close to full, then it'll get resized and things under the hood. You don't really see that kind of stuff. And so pretty much what happens is those are the kind of things that happen with a hash map. Is essentially you have some kind of hashing algorithm, you get an index, you put your key value pair in whatever data structure you hold in this index, linked list, array, or to the typical common ones. And then, like I said, as your hash table becomes more and more full, and you're very likely to hit collisions, then usually you make it bigger. Because you wouldn't want to make a hash table that's 1,000 elements, right? If you're only putting in 5, that just seems too much. It's okay to have collisions, so there's trade-off there, right? How many elements do I want to have in every single bucket? Obvious trade-offs, and then do I want to make it bigger, and so on. So now I'll talk about what our simple implementation is going to be. So essentially here we have, I think, 10 to the 6th insertions or so. So what I'm actually going to do is I'm just going to make it quite simple. I'm just going to make an array of 1,000 buckets. So we'll have an array of 1,000 buckets, and then every bucket will be another array. And it will be another array that will just be an empty array. And essentially then what we're going to be doing is we're just going to be putting in our new buckets into that array. So what would happen is, let's kind of go through how this would work for our buckets. So essentially we'll have an array of 1,000 buckets, right? And we're going to have a really easy hashing algorithm as well. We're just going to take the key and mod it by the length of our array. So we'll just take our key, mod it by the length of our array. It's going to be 1,000 buckets. And let's kind of walk through what would happen. So when we first initialize our hash map, we'll make our 1,000 buckets. Then we are trying to put in 1, 1 into the hash map. So when we put in 1, 1, what index is that going to go into? Well, that's going to be 1, mod 1,000, right? 1 mod 1,000 is just going to be 1. So we're going to put in into index 1, into this bucket here, we're going to put in 1, 1. So 1, 1 is going to go here. And we're going to store our, the way we're going to store our stuff is we're going to store it in an array, right? So we're going to store our key value pair in just like an array of 2 items. So this array is going to, right now, just be like this. It's going to be an array. It's going to have 1, 1 in it, and that's it. Okay. Now we try to put in 2, 2. And so when we run our 2 through our hashing algorithm, which is just the key mod 1,000, we're going to store it at index 2. And so now our array here will be just 2, 2. Okay. And then we are going to get 1. So when we get 1, what we need to do is we need to take the key 1, we need to run it through our hashing algorithm. Then we need to figure out like what bucket is it in. So when we run it through our hashing algorithm, we're going to check, okay, it's in this array here. Then we're going to loop through this array and look for key 1. So the first value needs to be 1, and we are going to find it. And then we can just return the value associated with that key. So we're going to return 1 here. Then we're going to try to get 3. And so 3, running through our hashing algorithm, anything less than 1,000 is just going to return us that number. So we're going to check in here for 3, and there's nothing in here. So because there's nothing in here, there's nothing to look through. So we're going to return -1 here. Then we're going to put 2, 1 in here, right? So to put in 2, 1, that's going to be an index 2. So this is going to map to here. And then there is a key 2, right? So there is a key 2, and we want to replace its value to 1. So we're going to change this to a 1, right? So put should change the value. Then we're going to get 2, and then that'll just go in here. We're going to get the value 1 out of there. And then we are going to remove 2. So we're going to look in here again, get this key, and remove it from the array, right? You can just do a pop. And then when we get 2, we're going to return -1 because this array will basically be empty. So essentially, we can also talk about our performance really quick. So for our put, essentially we have to look through our entire like bucket and check if it's in there. So that's going to be O of n, where n is the length of the bucket. Similarly, for get is also going to be O of n, where n is the length of the bucket. And finally, remove will also be O of n, because essentially we're going to have to look through our bucket. And then it's okay to remove through the middle because when we do the lookup, that's going to be O of n as well. So removing from the middle will also be O of n. So each of these operations will be O of n, where n is the length of our bucket. We will get to the bucket in O of 1, but depending on the length of the bucket, that part will take O of n. And that's essentially what we're going to have. And like I said, you could optimize this by having like a linked list, because with a linked list, you will have removals faster, but you still have to look through your linked list. You could probably make further optimizations. There's kind of just like trade-offs between space and time for these hash maps, right? The more space you make, the faster your lookups, but you're going to have more space. So there's trade-offs there. Okay, so we're just going to make a hash map of 1,000 elements, and then we're going to do our stuff there. So now we can kind of code it up and go through it. And like I said, you could make it a lot more performance-based by resizing when your number of empty slots gets kind of small, but that's going to be like way too complicated and kind of like not an easy problem. So first we're going to make our hash map. So we're going to say self.hashmap is just going to be a empty array, which will symbolize the bucket, and we're going to have 1,000 of those. So next, we are going to essentially try to put something into our hash map, right? So first, we need to get the index where to look. So we'll get an index. We can even get like I equals key mod 1,000, right? Our super simple hashing algorithm. Then we're going to get a bucket. So the bucket is going to be self.hashmap at that index. And now we simply have to loop through our bucket, right? So for I in range length bucket. Yeah, I guess it's fine to use I again. Okay. So essentially we loop through our bucket and we look for our key. And if we do find a key, then we update it to the value. Otherwise we append to the end. So if bucket I 0 equals key, And remember, in our bucket, it's just going to hold arrays of 2 elements, which will be a key value pair. So if we find the key, then we want to set the value. So bucket, say my value at index 1 will be the value, and we can return. Otherwise, if we don't find anything, we'll just add that to, we'll just add the key value pair to the end of the bucket. So we'll add it here. And then similarly, get is going to be quite similar again. So we can copy this code. And we can copy this code actually. So get will just loop through our, actually we can copy like all of this pretty much. Get is going to kind of do the same thing. We're just looping through our bucket. And if we find the key, we just, so instead of changing the value, we just return the value. So we return this, right? So same kind of thing. We get an index, we get the bucket, and then we loop through the bucket. If we find the key, we return the value. Otherwise, we return -1. And so get and remove are also very similar. So we're actually just going to copy all of this as well. So essentially same kind of thing. But now if you find a key, we want to actually pop this element, right? If we find a key, we want to pop it. So what we're going to do is we're going to say bucket.pop at that index. So we're going to pop it, and I think remove doesn't take in anything. So if we find it, we're going to pop and return. And then if we don't find anything to remove, I don't think we need to return anything either way. So essentially just to loop through this one more time. So we make our hash map that's going to be 1,000 buckets. And to put something in, what you need to do is you need to find the actual bucket that you're going to be putting into. So we can just get an index, which is key mod 1,000. We can get the actual bucket because our hash map has a bunch of buckets. And then we loop through our bucket. And if we find the key, we update the value. Otherwise, we just append it to the end. And like I said, with a linked list, this actually with a linked list, this wouldn't be any more efficient because you still have to traverse your linked list. So put would be the same and get would be the same. The only thing is this remove would be, so actually time complexity wise, remove would be the same in a linked list because you still have to loop through it. But this pop is inefficient in an array because we're popping from the middle. But because we have to worst case scenario loop through this whole array anyway, it would be O of n regardless. So we can try this and then we can go over space and time. So I think this is, we're getting an error on line 4. So let's take a look. It's to be in range. Okay, there we go. And you can see it's reasonably efficient. So let's go through the time and space for all of our stuff here. So what do we have? We have put, get, remove, and our constructor. So we'll call this constructor. So for the constructor, we make 1,000 elements. That's going to be O of 1,000. So that's constant, I guess. O of 1. For the insert, or the put, I guess. So we're looping through the bucket. So worst case, everything maps to the same thing. Yeah, everything maps to the exact same thing, right? But because the only way that can happen, right, is only keys, like the only way you can map to the same key, for example, key 0, like what would map to key 0 would be like 0, 1,000, 2,000, 3,000, and so on. Because we made our, because we have 1,000 buckets, this is actually like n over 1,000 technically, which does still round to, which still does round to O of n, but it in actual like time, it's going to be significantly faster, right? So if this was 10 to the 6th, then we would only have to look through 10 to the 3 elements. So we're saving a lot there. Okay, and then, or so I guess this is not the insert, this is like the put or whatever it was. And then get would be the same, O of n, and remove would also be O of n. Where, like I said, it's technically O of n, but in reality it's n over 1,000, which saves us a lot here. Okay, so now for the space, so this constructor is going to be technically O of 1 because we just said it's 1,000, but you know, maybe you could say it's like O of whatever. For put, so worst case scenario, like this is once again kind of weird. So technically, every bucket can get to, like worst case scenario. I guess actually in the we don't even need like put or get or anything. So worst case scenario, actually realistically, we're gonna fill up our bucket with every single element, right? So like every single element will fit. If we just have all puts, this will be O of n if we just have all of puts. Because we would essentially try to put in every single key from 0 to 10 to the 6th, which would give us n keys, essentially, or whatever. Like, if all the keys are different, and they all, I guess it doesn't matter where they map to, essentially. This is going to be O of n, roughly, though. Because space is O of 1,000, but then you can have all your keys, you can just keep putting in more and more and more stuff. So that's going to be O of n space. But yeah, so you could also do this with a linked list, where you can make a bucket a linked list. It's a little bit more performant, but not too much. But this is a lot more convenient. And then if you want the actual like better performances, but there are downsides, obviously, at least for space, is you can, instead of having 1,000, you can have this start off small and then resize when needed. But that's more like a real like super well made hash map, which is like beyond the scope of this problem. That would be like actually like how a Python hash map is made, where I do think it resizes similarly to an array. So worst case, actually your inserts can be quite a while, because essentially you have to put in every element again, because things might map to the wrong things, right? And I think actually there's like a bunch of other performance things where, like, if your current bucket is taken, it'll like add to a similar bucket. Like, this would be like a very, very advanced algorithm if you actually code up like the actual like Python under the hood dictionary. So, but for our case, simple hashing mechanism, which would also be, a lot more complicated than this in a real hash map and so on. So, but yeah, that's going to be all for this problem. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.